Hello everyone, it's Doug here, and in this video, which is the first part of a multi-part series here, we're going to talk about the oxidations of alcohols. And so for right now, I'm just going to introduce what oxidations of alcohols look like, their very, very general mechanism, and how we can look at like a primary alcohol or tertiary alcohol and predict what the outcomes will be when they're exposed to an oxidizing agent. So first of all, oxidation alcohols are an extremely important organic transformation. I'm always a little disheartened when I look at our organic chemistry textbooks because there's often like 1, 2, maybe 3 pages about oxidations of alcohols in a textbook, when in reality they're an extremely important reaction just because alcohols are so common in nature. And so we can oxidize them into new functional groups, which allows us to make new molecules. And then once we have carbonyls and aldehydes and stuff like that, carboxylic acids, then we have whole new functionalities that we can then go into. So it really is a huge gateway into a lot of functionality and a lot of different molecules. And that's why, for example, this is a book that I read a lot in grad school, Oxidations of Alcohols to Ketones, to Aldehydes and Ketones, by Tojo and Fernandez. It's or Toho and Fernandez. It is amazing. It's a whole book just on oxidations of alcohols, whether they're iodine-based desmartin pyridinane type stuff, or ruthenium catalyzed, or tempo mediated, or chromium-based stuff, which is not used all that much anymore. It's just an amazing book, and it got me through a lot in grad school, which is amazing. So, like for example, I was trying to turn this molecule here into this molecule here, and it took me months to figure out how to do it. I mean, I tried everything. I tried normal sort of stuff with like PCC, which we'll talk about later, which did not give me what I wanted. It gave me this weird cyclic ester thing. I tried other classic reagents like just straight up Jones that over-oxidized. I didn't really want that. I made my own desmartin pyridinane, fresh. It's explosive and dangerous. I made my own. That didn't work. What did end up working for me though was something called Swern, the Swern oxidation, which we'll talk more about later. But there's a ton of different reagents out there. We're gonna look at like 4 reagents more or less that are just really common in organic chemistry, partly for historical reasons and then also partly for green reasons and application reasons. They're starting to find themselves in more and more textbooks. And these are just ones that you're likely to see in like an ACS test or something like that, or any other materials from the book. So let's talk more about the general mechanism here. The idea, if you look at this mechanistically, is that what happens, and I'll show you more real mechanisms in future videos, but more or less what happens is you get something that's some sort of base or slightly basic. It might even be just water, for example. And what's going to happen is that something is going to react with your H to make it a better leaving group. So this H on the alcohol becomes a better leaving group. And so what we end up seeing happen here in the general mechanism is that some sort of base ends up removing this hydrogen. These electrons go to form the double bond between the C and the O, and your H goes. And so what you end up getting here is the R group is still attached to the carbon, as is the other R group. That oxygen is still attached to the carbon, but now it's just double bonded to it, right? So we went from a single bond to the OH to a double bond. In this case, it was a ketone if these R groups are Cs, but that's not that important right now. The point is we went from having something with just 1 CO bond to now something that has 2 CO bonds, right? There's a double bond, we count it as 2. So that's what oxidized it, right? This would be an oxidation. Now, if that's real general, this is not a mechanism that you're going to show me on a quest or an exam or anything like that. But this is just the general idea of what happens. And the main reason I'm showing you this is to highlight the fact that what's really important here, what we see is involved in this mechanism, is that I need to have a carbon that has an OH on it and an H on it, right? That's the reactive part. That's the thing that I can oxidize. So if I want to know if I can oxidize up an alcohol, that's what I'm looking for. I need a carbon with an OH and an H. So for example, I have a list of different types of alcohols down here. And if we take a look at these different types of alcohols, we can name them, right? It's kind of like, you've done alcohol, or like alcohol halides, right? We talked about like a primary alcohol halide or a tertiary alcohol halide or a methyl alcohol halide. Same thing for alcohols, right? So for this first alcohol, since the alcohol is on a carbon that is not attached to any other carbons, this would be considered a methyl, right? This would be a methyl alcohol. This alcohol right here, it's attached to a carbon. There's only one other carbon there, so that would be a primary alcohol, secondary alcohol, tertiary alcohol, right? Because this bottom one, the OH is attached to a carbon. That carbon is attached to 3 different carbons, so it's a tertiary carbon. So we can have, primary alcohols, tertiary alcohols, etc. If I want to know if I can oxidize these different types of alcohols, again, what I'm looking for is a carbon with an OH and an H. So for example, with the methyl, that's exactly what I have, right? I'm going to square it off. Here I have a carbon, there's an OH directly attached to it, and there's an H directly attached to it, right? That's the part that reacts, that gets oxidized, and turns into our carbonyl. That's the part that turns into the carbonyl, the C double bond O. And then whatever else was attached to that carbon just kind of comes along for the ride. So in this case with the methyl one, it was just an H here and an H here, so I'm just going to draw those back on to this. So in this case, my methyl alcohol got turned into an aldehyde. And that's all that we're going to talk about for right now. We'll talk about what reagents do these later. If I go down to the second one, the primary alcohol, I'm going to ask myself the same question. Do I have a carbon that has an alcohol group, a hydroxyl, and an H? And yes, sure enough, right, I've got the same sort of thing. So I can square that off. That's the carbonyl. And again, I bring along the 2 groups. The only difference with this one is that one of the groups is a methyl, and the other one is an H, so that gives me another aldehyde. If I take a look at the third one, again, do I have a carbon with an H and an OH on it? Yes, I do. So carbonyl, and then you bring on the extra 2 groups. In this case, I have 2 methyls, which means this is not, right, an aldehyde anymore. This would be a ketone. So I can get aldehydes or ketones. It just kind of depends on what the alcohol is and what you end up making. And then if I go down and I look at my tertiary alcohol, I've got a carbon with an OH attached to it, but that carbon itself does not have an H attached to it directly. It only has a carbon and a carbon and a carbon group, right? So since I do not have a carbon with an OH and an H on it, this one is going to be no reaction. We cannot oxidize tertiary alcohols. So cannot oxidize tertiary alcohols. They do not have the hydrogen that needs to be plucked off in order to make that carbonyl. So they just, no matter what, no reagent, there's no reagent out there that's going to make a tertiary alcohol magically turn into a ketone or something like that. Now the question is, can I only oxidize all of these once, right? We would consider these all one oxidation. This went up one oxidation state. Put a little oxidation symbol in there. I want to know, can I keep on oxidizing these? Can these oxidize twice, 2, 3 times? Like how many times can I oxidize these? Can I go further? And if I took a look at this right now, the answer would be no, right? I would say no, I cannot oxidize this one any further. I'll write this down. No, cannot be oxidized further, right? And that's because there is no carbon with an OH and an H attached to it, right? I don't even have an OH in that aldehyde, that formaldehyde up there. There are H's attached to the carbon, but there's no OH. There's no OH in any of these. So right now the answer is no, none of these can be oxidized any further. But of course there's a little catch. We need to talk about what happens if water is around. So if this is a reaction that's kind of getting ahead of us, so I'm just going to tell you what it is. What happens is anytime you have a carbonyl compound, and they do these to varying degrees, but anytime you have a carbonyl compound, if it's like an aldehyde or ketone, for example, and you have water present, there is going to be an equilibrium in which you form something that's called the hydrate. And hydrates are just when you have a carbon with 2 OHs on them. Or in other words, sometimes these are called geminal diols. So I'll put AKA geminal diol. Right, it's when you have two OHs attached to the same carbon. Now, if you notice that my little equilibrium arrow up here, I have it going much more to the left than to the right. And that's because this is still the main form, right? It still mostly looks like the carbonyl compound. It's just that water adds in for a small amount of the time, or a small amount of it gets converted to this hydrate. And it's a dynamic equilibrium, a normal chemical equilibrium that goes back and forth. But what's interesting about that, right, is we said when you had an aldehyde like this one, right, we said that if you take this, for example, this was what, your methyl alcohol. I think I used blue here. I don't know if it matters. If I take my methyl alcohol and I turn it into this aldehyde, we said that I could not oxidize that aldehyde anymore because it doesn't even have an OH. But what I want to introduce here is that if water is present, the idea here is that there's an equilibrium with water and this aldehyde so that I can turn this aldehyde into the hydrate. Right, where again the idea here is that the elements of water, two hydrogens and an oxygen, add in to make the hydrate, and that's just an equilibrium thing. But even though it's just a little bit of stuff, as soon as you have that OH and that H, boom, you can do the oxidation. Just like we circled off the OH and the H before and turned those into carbonyls, it's the same exact idea here. And it's also similarly true that the two things that were attached just stay attached. So in this case, I had an H and I had an OH. And so that allowed me to turn my aldehyde, in this case, up to a carboxylic acid. Turns it into a carboxylic acid. But again, that's only if there's water present, because when water is present, I can make this hydrate intermediate here, square off my OH and H, and do that oxidation so that I can get the carboxylic acid. And if I take a look at the one below here, right, so here's my primary, I'll label these right now, my primary alcohol, my secondary alcohol. I didn't put the tertiary one back on here because it doesn't matter. You can't oxidize tertiaries at all. But the same thing, right, if I take a look at this one right here, and say there's water present, right, so say I have some water present. Now I've got my CH3, attached to a carbon, attached to an H, attached to an O. If I form a little bit of hydrate, the question is, can I do an oxidation on this? Can I do an oxidation? Do I have a carbon with an OH and an H? And with this one, yep, sure enough, I do. I'm going to turn that stuff into a carbonyl and then add the remaining pieces. So in this case, a CH3 and an OH, and again, I form a carboxylic acid. But again, just if I have water. And then I'll do this last one, right? So I had this ketone down here. Right here we had a ketone. Same deal. If I add water to this, I'm going to get a CH3. Sorry, it's hard to write the bottom of the screen. There was an O. I'm going to add an H and an OH. Ask myself again, can I square off an OH and an H? And in this case, I cannot, right? This is not going to be oxidized any further. I do not have an OH and an H attached to this carbon. I do have the carbon. I do have an OH, but there is no H attached to this, so I cannot oxidize it any further. So ketones don't really go any farther than this. They just kind of stop there. I can't continue. Now, what happens? I mean, can I do any more, right? So I had the first oxidation. So let me write this here. Let's write the first oxidation check, first oxidation check, and first oxidation check. Now looking at this one, it looks like I could in fact do, right, this was the second oxidation. This one was able to do a second oxidation, but this last one was not. Could not do a second oxidation. Stuck, done. But my methyl alcohol, this one at the very top here, can I keep going? If I have water, can I form another hydrate, do another thing? And if I take a look at this one, I'll do the same deal. I've got an H, a carbon, an OH, and then oxygen here, turn it into the hydrate, right? So I'm adding another thing of water. Can I oxidize this one further? Sure enough, I can. I can square off an OH and an H, which again is going to give me a carbonyl. And that will, and then I'll add the other two pieces. So here would be the other arrow. Looks like it still has an OH on it and an OH on it. And that's carbonic acid, or you may remember from random Gen Chem trivia, that's carbon dioxide, right? Basically, you lose water, you lose the two OHs, and it turns into carbon dioxide, turns into C double bond O, C double bond O. So you actually can oxidize that one a third time. Third oxidation. But if you take a look at it, I won't go through it, but if you take a look at the primary alcohol one right here, you'll see that this one also does not work. This one would be no reaction, so you can't oxidize that one any further. Another way to look at this, if you're wondering, like, well, how many times can I oxidize it? A kind of a trick that you can do is you can come back to that original alcohol, and like for my methyl alcohol, I have 1, 2, 3 hydrogens on that carbon. So this is potentially, I can do up to 3 oxidations, which is what we saw here, right? I saw a first, a second, and a third oxidation to get all the way over to the carbon dioxide. If I look at the primary alcohol, it only has 2 hydrogens attached to the carbon where the alcohol is. So that's, you can do up to 2 oxidations for that one, which is what we saw, right? I only saw the first oxidation, second oxidation. I stopped here at the carboxylic acid. And then lastly, for the secondary alcohol, I only have 1 hydrogen on the carbon with the alcohol, so up to only 1 oxidation in that case, which is what we saw. We could only go up to the ketone was the idea. So you can also get kind of a sense of how many oxidations you can potentially do by seeing how many H's are on the carbon with the alcohol group itself. So let's take a look at just some generic examples. So here I have 4. I'm going to go ahead and label these primary, secondary, tertiary, quaternary, whatever type of alcohol they are. This one, actually maybe you should pause for just 1 second, label what these alcohols are in your notes. So if I was to look at these here, right, so this one's definitely a tertiary alcohol, secondary alcohol, primary alcohol, primary alcohol. Now you can remember just because for trivial reasons, or you can look at this carbon here and see that, hey, this carbon where the alcohol is, there are no H's, which means I can do no oxidations, right? And remember we said before that tertiary alcohols can't be oxidized at all. So it's just flat out no reaction there. If I take a look at my secondary alcohol here, there is 1 hidden H here, which means I can oxidize it, but really only 1 time, right? I can only oxidize it 1 time. If I look at my primary alcohol, it looks like there's 2 H's on here, so I could oxidize it once or twice. Here on this primary alcohol, I could oxidize it once or twice also, right? So up to 2 oxidations for these last 2. Since on the secondary alcohol, since I'm going to go ahead and I'm going to square off or circle off my H and OH here, right? I know that that's going to become my carbonyl, so I'm just going to redraw the organic piece, and where that OH was, now I'm just going to draw the C double bond O, right? That carbon right there, that carbon number 1 is now going to be where your carbonyl is, and that's all I need to do. Just 1 oxidation. It has 1 more bond to oxygen, right? This has, as far as CO bonds go, this only has 1 CO bond. Now this has 2 CO bonds. And yes, there's water present apparently, but that's not going to allow me to magically have more hydrogens on that carbon. It's just providing me with more OHs in case I need them. So whether or not there's water there or not doesn't change the fact that a secondary alcohol is only going to be oxidized to a ketone no matter what. Now for these secondary ones, these two identical alcohols down here, the big difference here is that one has water and one has no water. So that's going to change how many oxidations I can do. That's really the big difference, is how many oxidations you do depends on whether or not you have water. If you have water, you oxidize it as far as you can. If you don't have water, you can only oxidize it once. So for this one, right, I'll do this again here. I have an OH and an H that are going to get turned into the aldehyde. So if I draw that structure, it's going to look something like this. Where I left that H on there, that was one of the green H's. But since we have water here, right, we know that I can turn this molecule, that this molecule in the presence of water is also going to look like this. And that means that I can square off another OH and H to turn it into the carboxylic acid. And that would be my final product. So I did the first oxidation, and then I did, right, first oxidation was from this to this, second oxidation was from that to that. Right, so I did two oxidations, or another way to put it was that this had one CO bond, and this now has 3 CO bonds, right? I did two oxidations. I went from 1 to 2 and 2 to 3 bonds to oxygen. Now for this one where there is no water, same sort of thing occurs. Well, that was supposed to be purple, that's okay. Same sort of thing occurs, I square that off, now I form the aldehyde, but now since there's no water, I don't have the equilibrium, I don't have any hydrate like this, right? I don't get that hydrate, so I just stop. And for this one, that's the product. You only do one oxidation. This is the first oxidation and the only oxidation. It could be oxidized further if there's water, no more oxidations. So that's kind of your introduction to oxidizing these alcohols. In the next video, I'm going to introduce some actual reagents like PCC and Jones and Swern and stuff like that. So take a look for that video and then start your practicing. Happy studying and good luck.